Yeah. Okay. So sorry for that. So I'll
Yeah,
start screen
and
share.
also, let's just one moment. Have to, okay, I mean, since I won't be, I'll also start recording on this. And I think you should be able to, yeah, I should also be able to stop the recording, yeah?
Yeah. Okay. But I don't see an option on my end right now. I think maybe I can record on my end as well.
Why don't you do that? Yeah.
Yeah. Sure. So I'll record on my end. Yeah. Okay. So I think recording has been started and we're live on YouTube. So let's start. Um, so basically this today's tutorial will be on setting up Marabou and using it. So let me go to the first place that you'll probably need to go, which is the Marabou GitHub. So you just search Marabou on Google, or I'll also of course put this link on Google. And the way that you, or the things that you need to do to install this is basically you'll have to just download and build it. There is no other way. Okay. So I'm not sure if I'll be able to show the build live because it might take some time. But what I will do is I'll download one instance of Marabou and start building it at least. And then you can see like what the process looks like. So if it takes more than a few minutes, we'll stop it and go to whatever instance I had already installed. Okay. So, of course, you can use whatever method you usually use to sort of copy or clone GitHub repositories. You can clone it by HTTPS like I'm doing here, or you can use whatever you would normally use. Just a second. Right. So here I'll clone this. So yeah, as you can see, it is kind of big, not too large, but like you will have to sort of download this and install this and all of that. Right. So now that you have cloned this, you'll see that there is a Marabou folder over here. This is the folder that basically contains the repository from GitHub. And now inside this, what you need to do is you need to basically start the build process. So to start the build process is CMake build, right? So if you're familiar with C, C++, this will be sort of familiar with you, familiar to you. So what you need to do is you need to make whatever the build directory or whatever that you want to make. So what they suggest over here is to make some sort of a build directory. And in there, you'll have to set up your build using CMake, right? So let's make this directory. Make this directory can have any name, but this will have all the compiled binaries for Marabou and also the bindings for Python and so on, right? And inside here, what you need to do is you need to do, so what CMake does is that CMake is basically something that generates a build script. Once the build script is generated, it's usually a make file and you can use make to then actually run the build, right? So CMake will configure your build for you and generate a build script according to your configuration. And then make will actually run the build for you, right? So there's these two steps. Now, of course, if I like, if I want, I can do all sorts of very specific configurations. I can turn off various features of Marabou or turn experimental features on that are turned off by default and so on. But for our purposes, it's fine to go with the default build. And for that, you just need to do CMake and then you point it to the parent directory. So you need to point it to a directory that contains the cmake list.txt, right? So right now we are in this build directory inside Marabou, and Marabou contains this cmake list.txt file, right? So right now we're in an empty directory. And if you look at the parent one, it contains this cmake lists file. So you need to point cmake to a directory that contains this file, and we just do it like this. And then cmake is going to essentially set up or detect whatever you have, whether the build is done or not, right? It will install all the dependencies. It will check your system for any other dependencies that it might need to install, and then it will configure the build script and generate a make file. That will take a few seconds, hopefully more than that. Right. Okay, so right now it's downloaded this.
Can we use
Yeah.
CMake on Windows?
Yeah. There is a GUI for CMake on Windows, if I'm not wrong. Um,
Okay.
I'll show you something. Right. So there's this cmake.org, and you can download CMake from here. And then there is a really nice looking GUI that will show you a lot of options that you can turn on or off and so on. I think the one that you would probably want is either this or this, whichever you prefer. I think both of these will work. There's an MSI and there's a standalone zip, right? So you can install CMake via this or that.
Okay.
And I think on Windows, CMake doesn't produce like a make file, but rather it will produce, depending upon what you want, it can produce a Visual Studio solution that which you can then open in Visual Studio and build. Or it can also produce a make file that you can then, there's a Windows version of make with which you can build that as well. What these guys suggest for Windows is using Virtual Studio, right? So then you can, once you install CMake, if you run this in a command prompt, it will produce a Virtual Studio compatible sort of solution. And then you can open that in Virtual Studio, or you can just use CMake directly to build it. Is that okay?
Okay.
Yeah. So
Yeah.
So right now I don't have Windows on me, but like if you have any issues with getting this installed in Windows, just let me know and I can help you out. Okay. So okay,
Yeah, sure.
so this is right now taking some amount of time. So what we'll do is we'll parallelly I'll go over the interface for Marabou. Okay. So let me just create and I just copy an existing Marabou folder that I've already installed. And while that is copying, let's look at the docs for Marabou. There is some official documentation for Marabou Pi, but it's sadly not very comprehensive. So Marabou Pi is the Python interface for Marabou, which is what we'll be using. There are several examples over here. There is all of these examples, but I think the most relevant to us would be basically this page over here, the Marabou code example. And again, I'll link all of these, right? So here what they do is they take one, set of constraints that represents a network, and then they add it step by step to Marabou, right? And we'll basically be following this. So can you read this, by the way? It's the font open.
Yeah, yeah.
Okay, so we'll basically just be following this. Yeah. Hello?
Was there a question, Nabeen?
No, I was just saying that I can read it.
Yeah.
Oh.
Sure. So basically, we'll be following this and setting up Marabou that way, right? Okay, let me see if this copy is done. So fine, we'll just go over here now. Right. So again, right now the build process of Marabou is happening, and after that there is another, like this is the CMake double dot step. After that, you'll have to do a make step, and this is all there in the GitHub. So I'll show you that step because I don't think it should take so long that we won't have time. But let's parallelly start writing some code that will use Marabou, right? So yeah, so anyway, so this is sort of the next step, sort of. You do once you've done CMake double dot, then you can do either CMake double dash build, which will start the build process itself. And then there are several sort of options that you can pass to it, right? So once this is finally done, you need to type in something like CMake double dash build. Okay. So these are the two steps important. So then you'll basically have this folder called Marabou. And if you look inside this folder called Marabou, you will have, and remember, this is another copy that I had lying around. So you will have inside this folder, another folder called Marabou Py, right? And inside this Marabou Py, you will see you have a bunch of Python files, right? These Python files are basically serve as an interface for the C++ API for Marabou. And this is what you will use when you want to access Marabou via Python. So to do that, firstly, let's create some very simple Python script, right? And just that you're not confused, this this box over here, this represents the terminal. So I'll just hide this actually. Yeah. Sorry.
So, but Marabou does not have a GUI-like interface where you could.
No, it does not.
Does not.
Yeah.
Okay.
Yeah. In fact, its Python interface is also very bare bones. It doesn't have any too much error support as well. So that way, the interface is not very like polished, but yeah, it is.
Yeah, but does it give counter examples?
Yeah, it does give counter examples. You'll have to extract it from. It'll give you a result struct, and you'll have to extract it from there.
Oh, I see. That also you have to use.
Yeah, the Python interface for it.
Interface for that.
Yeah.
You don't have a ready-made extract model or something like that.
Right. Yeah. So I mean, they'll give you sort of assignments for all the variables, and then you'll have to extract it. Yeah.
You probably show that, no?
Yeah. I'll show that. Yeah. Okay. So the first step to using Marabou is to actually getting it to import, right? So for that, what you need to do is you need to add this particular folder, this Marabou folder that you have to your Python path. Are you familiar with what a Python path is, by the way, Naveen? Hello.
Could you repeat the question?
So do you know about the Python path? So basically, it's just a environment variable which has several locations in which Python searches for imports by default. So whenever inside your Python you do something like import and then foo, it will search for foo within a specific set of locations, right? There'll be some system directories and there'll be some directories in your home folder. Yeah, so that is your Python path, right? So right now, Marabou is just sitting somewhere in our system, right? So even though there is a Marabou Py folder inside this, if we just do say something like import Marabou Py, Then I'll just have a print statement here just so that we know that something has been done. And then if I try to run this script, see, it can't find Marabou.py, right? It says module not found.
Yeah.
You'll have to point Marabou towards, or point Python towards this Marabou folder. So, and the cleanest way, there are several ways of doing it. You can permanently change your Python path to have this Marabou folder in like wherever it's installed, right?
So I can't actually see the top line, the import line. There is something like over it.
Oh, okay. Sure. So the import line is just this.
Yeah.
Can you
Okay.
see the code? Yeah. So I mean, so you can sort of, one of the things you can do is sort of set up your system's Python part to always point to Marabou. And if you're on Linux, you can do that by uh, putting a export line into your bash RC. If you're on Windows, you can do that by, I think, somewhere in the command, like somewhere in, if you click on my computers and then properties, somewhere like that, there should be something called environment variables where you can change things like your path and Python path and so on, right? That is one
Yeah.
way, but the way that I found, which is I think a little bit like, at least I find this easiest, is that you can sort of just set up your Python path inside the script itself. So you can import OS. I think it's, yeah. And then you can do sys.path, which is your Python path, and then you can append the name of the folder. And this can be a relative path to the name of the folder that you have, right? If I do this now it has found Marabou, right?
Yeah.
So now we have imported Marabou, right? So now the first thing that we have to do, if you remember in Z3, that sort of the way your code ran was that you created a solver, you added constraints to the solver, and then you queried the solver, right? It's the exact same over here. The first step is to create a solver, and the class that represents the solver is called a Marabou query, right? So we have to import that from Marabou.py. So inside Marabou.py, there is going to be a class called Marabou query. And then we can create an instance of that. So if you look at the docs over here, see there is this module called Marabou code inside Marabou.py, and from there you can import an input query. An input query is basically what your solver is in this particular case, right? So let's do that. Right? So input query is basically the equivalent of a solver in this particular case. And here, let's set up some solver, right? Okay. So this is the first step. Now, the next step that you'll have to do is you have to set the number of variables. So in Z3, if you remember, once you created the solver, Z3 had a very nice interface where you could just create variables and then build expressions using them just as you would in Python, and then just pass that to the solver, right? Unfortunately, Marabou does not have any such nice interface. It doesn't allow for you to give it a bunch of arbitrary expressions. It expects expressions in a particular form. And very importantly, you'll have to specify the number of variables you're going to use in total upfront, right? And you cannot change this later on. So you'll have to, as the first thing that you do with your solver, you'll have to set the number of variables that you have. So you do this by, and again, I'll just refer to here, this particular function. Right? And you set up, say, number of variables. So now that we're at a point where we have to set up the number of variables, we should sort of decide what we will model, right? So let's take a very simple neural network. Right. So let's say that we will have a very simple neural network, which has got one input, two ReLU neurons over here, And then let's say that there is going to be one output, right? So let's give these variables a name, correct? So we'll say that, and actually, you know what, let's maybe even split this thing into pre-relu and post-relu. So yeah, this is a relu operation. This is also relu.
Yeah, but I
And
think it's
then-
very important to have pre and post relu, because relu plex really makes a distinction between those two pairs of variables, no?
Yeah. In fact, you can't model it in reluplex, or you can't even pass the network into reluplex without having pre and post pairs.
Yes. Yeah.
It's like it's necessary to have.
As they call forward and backward variables. Okay?
Right. So let's basically name our variables. So let's say the input is X, the output is Z, and let's say that this one is okay. You can still hear me, right? Hello.
Yes. Yeah.
Yeah. So let's say there is YF1, YB1, and YF2, YB2, right? So for the forward and backward variables. So now, how many variables do we have? We have 1, 2, 3, 4, 5, 6 variables in total, right? So we can basically, we'll have to decide this beforehand. So, but now that we have decided this, we can basically just set the number of variables to 6. Now we need to add a few constraints to this thing. So there's two kinds of constraints that we'll need to add, right? One is linear constraints, and the other is relu constraints. Right? So let's look at how you can add these two things. And again, let's go back to the doc. And if you go into the API documentation, and if you go into Marabou code, there you'll be able to see there is this one particular class called Marabou code.equation, right? And this equation is what you will let you add in linear constraints, right? And then you can sort of set up an equation using this add-end, and then add and set a scalar, and this will basically set an equality constraint for you, right? So let's see what kind of equation constraints that we want, or linear constraints that we want, right? So we would want to say, let's set up the weights of this network to something. Let's say that this is 1, this is -1, this is 1, this is 1, right? Right. So now let's say that we want to set up a constraint which says y is equal to, or y forward 1 is equal to x, right? So this is an equality constraint. Right? So if you want to set this up, what you need to do is you need to express it as an equation of this form, an equation where you have a some constant times each one of your variables, and you have a sum of these, and you're then going to equate it to some scalar, right? So your equation is going to then be given by some number of constants multiplied by some variables, and then the final sum is going to be equal to some scalar, right? So the way you do that is by basically calling this add-end function, and this will take in, the first argument is going to be a float, which is basically going to be your coefficient over here, and then the second argument is going to be the index of this particular variable, right? So now we come to the way Marabou handles variables. In Z3, we had something very nice where we could actually talk about variables in terms of their string names. We could assign a variable or store the reference to a variable in a Z3 as a Z3 expression in a Python variable, right? So we could say something like x is equal to Z3.int, and then some variable name, right? And then we could refer to this particular variable by this name or by just referring to this Python variable, right? Unfortunately, in Marabou, you don't have any such nice interfaces. You have to refer to variables by integer indexes. So Marabou doesn't know what X is, what Y is, what Z is. It just, whenever you set the number of variables, it just assumes that, okay, in whatever constraints that you'll follow, you're going to pass it variable indices, and that is how it's going to remember which variable is what, correct? So you have already told Marabou that you're going to use 6 variables, and now you yourself have to keep track of what these 6 variables are. So if you have to give an index in your mind or in some other part of the code, you have to sort of keep track of the indexes of each one of these variables, and then make sure that you pass those correct variables when you're building the constraint, right? So let's fix some indexes for our variables right now. So let's see. Let's say x, yf1, yb1, yf2, yb2, and z, right? So our variables will be ordered in this way, and then we can set the indexes to be 0, 1, 2, 3, 4, and 5. Okay. So is this okay? And then what do we need to do to add this equation constraint is to basically...
Yeah, I guess you could simplify this by storing those indices in an array which corresponds to these things.
Yes, definitely. Yeah, we can definitely do something like we can have a dict that maps, say, a variable name to an index, right? In fact, let's do that in the code itself, maybe, so that we can keep track of things better.
Yeah, I guess, I mean, it's understandable. See, Marabou and ReluPlex, they are more like a research tools, okay? And they're not production quality tools.
Yeah, and I think they...
Yeah,
and then the other thing is that they don't really expect people to use Marabou or...
It's okay. Let's not get sidetracked. I mean, so just with the time that you have, so I'll...
Right.
I don't want to sidetrack the discussion to... Yeah. Okay.
Right.
No, but you don't have to show it like this array. I mean, unless you want to. Okay, because I'm just made that as an observation. That's all.
Sure, but I think that is actually a good idea. Maybe. So I don't think it will take too much time. Right. Okay. So now we can say 1, 2, 3, 4, 5. And then this is sort of, we can have a dict like this that is taking variable names to indices. But the main point is that you have to keep track of something like this, right? Marabou doesn't do it for you. So now let's go into adding linear constraints. So the way you add linear constraints is that you'll create an equation, an instance of this equation class. Then you'll add each, so it went to the, and then you'll add each sort of this A1, X1 pair over here. Each A1, X1 pair, you have to add it as an addend, and then finally you have to add the scalar, right? So let's say that we're going to add equation 1, which is, let's say that yf1 is equal to x, correct? And then we'll create a new equation class. And again, this is inside Marabou code, so we'll have to import this one as well. Then now we can, so to express basically this equation in this particular form, we'll have to write it like yf1 minus x is equal to 0, right? So our coefficients is So we have one coefficient 1 for the variable yf1. We have one coefficient -1 for the variable x, and the scalar is just 0, right? So let's add these things to our equation. And again, if you look at it, it's addend. The first thing you want to add is the coefficient. So that is the coefficient 1. And then we have the variable yf1. So that is this. Then this is, if you remember, it's just the index 1, right? And then we have x. And then we have to do a set scalar. Okay. All right. So this is one equation constraint added. Any questions so far? Say no, no. This is just you there.
Yeah. I understood.
Okay. So yeah, so let's just quickly copy this code and add in all the other rest of the equations that we have. The other one will be yf2 is also minus yf2 minus x is equal to 0. And then similarly, we have the second layer's constraints. So yeah. Right. So equation 2, sorry, will be, okay, so actually I've forgotten something. Of course, you have to add this to your input query, right? So if you go into input query, there is this thing called add equation constraint, if I remember correctly.
So similarly, you will have to do for all the inequality constraints.
Yes, so for inequality constraints, what you'll have to do is you'll have to set up a slack variable and then set bounds on that. So I'll talk about that in a bit. Yeah, so
which means you have to create equations defining the slack variables, and then then you have to set the bounds for those.
Right.
Things. That's how you will have to do it. Okay.
Yeah, so I'll show that.
Yeah, and then I have, I'll ask. I mean, I'm sure you have an order in which you will be doing, but I have. You can show that, and then more important questions is: do these ReLU pairs, the variables that denote the backward and the forward, are those variables treated specially?
No, they're not. They're not.
No. So the reason is, I remember the ReLUplex algorithm. Okay, I guess it internally already assumes that the forward variable has to be greater than or equal to 0. That constraint you have to specify, or it is already used, because the ReLUplex algorithm adds that constraint. Okay, so
yeah, so they manage that constraint internally. You don't have to add that.
So which means when you specify them, you just leave them as unconstrained, in the sense their bounds will be minus infinity to plus infinity.
Yeah. And then ReLUplex will like automatically derive those.
Yeah, but then you have to tell them. I mean, you have to specify them when you specify bounds on the input variables as part of the bound specification. Correct?
Yeah, exactly. So the input variables, the bound will be there on suppose, for example, in this case, we'll have some bounds on this particular input variable. And then bounds on all of these variables will be derived. And then you can have some post condition on this particular.
You have to define the slack variables also.
Yeah, but in this particular case, we don't have to define any slack variables, because all the things that we have are
correct. They're just equations. You're right.
Yeah.
Did you understand that, Nabeen? See, because all of them are equations here, except the constraint on the input layer and the constraint on the output layer. No? So that's why there is no inequality constraints involving these variables. No, but then that's all the more reason that these forward and backward variables of a ReLU pair are not input or output, but you still have to specify the bounds for them. No?
No, you don't. They are derived.
Oh, so you can just leave them. If you don't specify
Unconstrained.
any bounds, they'll just assume that it can be anything. Okay.
Yeah, and but you know the algorithm will still only
The
return
algorithm
something.
will right, of course.
Right. Yeah.
Okay. Good.
So
I'll be
right. So
leaving in 15 minutes. Okay. So I don't know how much longer you want to go because I'm sorry.
yeah, no, definitely. So I'm actually I think the time for this tutorial was also until 7:30, right? I don't remember.
I
But
think because it will be late for them to do that. So maybe you can.
right. So I think
Nabin is cooperative, then whatever time he sets is what you will have to go by.
yeah. So Naveen, tell me, like, can we go till like say 7:45? Is that okay with you? Or does dinner
Yeah,
start? Yeah, okay, sure. All right, so I'll
yeah.
not go
Dinner
beyond.
starts at 7:45.
Okay. So is that too late then?
No, it's fine for me.
Okay,
But
sure.
I think
When does
Jyoti
the
is also here.
cafeteria close for dinner?
I think it closes
What?
at 9.
It goes until 9.
Yeah, it closes at 9:15,
Okay.
Hmm.
I think, or
Yeah,
9.
but if you don't go first, then often you know
The
the
food
good
is
things are
over.
not
Huh?
there. Yeah,
Uh,
yeah. So I'll not
What is
eat.
the advantage?
Yeah.
What is the advantage using Marabou over Z3?
Yeah, see, so the main idea is that
okay.
with
So
some
I think you should. Yeah. No.
Hmm.
You should answer it very simply. You should not get sidetracked with that. Okay.
Yeah. This
So
is a very good question, by the
that's a
way.
very good question, and I think I've partially answered in the thing. And your two, I mean, my 1 cent's worth. Okay. I mean, I let Diganta answer it. Okay. So, for example, in your problem set assignment 2, part 2, I have some questions that contrast the two. So the number of case splits, okay, that you will have to do, it tries to optimize on that, okay,
Yeah.
because it has to consider the cases when the input to the ReLU, okay, this y, the backward variable. Oh, I mean, I think Diganta has it backwards. Okay, so
Yeah.
So, but in any case, the input to ReLU, you have to consider the two cases when it is less than 0 and greater than or equal to 0. Okay, so in some cases you will have to do that split. What Z3 does is maybe in theory it does those case splits. Okay, whereas in ReLUplex, it sometimes when it doesn't matter, if you can prove the property regardless without actually doing the case split, it does the it gets you a proof without the case split, and that is what all these addition new rules. So it is not just the simplex rules; it has all these rules to fix the value. It starts with YF and YB being unconstrained, and then it gets those bounds in such a so as to not only satisfy all the other equality constraints here, but also the ReLU constraints. Okay, and that sometimes you can do without case split. And if you follow, yeah, so that is that is the thing. Maybe I didn't bring out in my yeah. So okay, go ahead.
Yeah. So I guess one main reason why ReLUplex, so the advantage if you're looking for it is ReLUplex is faster, and you'll see that in your assignment. And the question, I guess, which sir, I think there's a lot that can be said in terms of why it's faster, but I guess it'll be one summary of it is what sir said essentially, that Z3 or something like that will explore more combinations of possibilities of certain variables being positive and certain variables being negative. While ReluPlex, since it's already very tightly integrated with Simplex, if you have fixed certain ReLUs to be something, then it will very quickly show you that, okay, that particular ReLU now has to be negative, this particular ReLU now has to be positive, and so on. So you'll basically, one decision that you do doesn't cascade into a number of consequent decisions. It can, like, using just one decision or one guess, you can already explore a large part of your search space by fixing other things. So that is the intuition. Is that okay?
Yeah, but I think it boils down to reducing the number of k-splits. Okay.
Yeah.
So you try to delay doing that k-splits and see if the simplex you can, because see, simplex also provides, several solutions. You kind of leave these backward and forward variables unconstrained, and then you try to solve it as just a simplex problem. Okay. And if you get lucky, if the simplex solution, that it derives is such that it already satisfies the ReLU constraint, mainly it is for the property. Okay, it is also property dependent. Okay, maybe the property that you want to prove at the output may be such that there is a satisfying instance, the same satisfying instance for all the values for the variables work for both cases. Okay, for the less than when the input to ReLU is negative and the input is non-negative. Okay, then you don't care. Okay, if the satisfying instance that you're looking for is such that it is something which works for both cases, you may get lucky, and then the simplex might provide that, and then you can get away without actually splitting the proof and exploring in your search both those cases. Okay. And that can happen using these things. And of course, that is not always guaranteed. Okay, so there is a lot of flexibility in the strategy that you use. Okay, so there is in the way that you apply all these ReLUplex rules, okay? Which solutions use simplex and so on. So both of them in the worst case can end up considering all possible cases. Okay, but in practice, ReLUplex works faster because it can optimize on those things through its strategies.
So I think maybe we can explore this question in like quite a bit more detail.
I think we should. Okay, in one of the classes, let's do that. Okay, so I think, but
But right now, I think I'll just go over the code and all.
I think so. I think
yeah.
I think this is a very good question, and why it does is something that we should explore. And once you try and answer, if you attempt a couple of questions on the part 2 assignment 2, it exactly forces you to think about this problem. Okay.
Okay. So yeah, so let me add all the rest of the constraints. So rest of the constraints just say that YF1 is equal to Z, or sorry, Z is equal to YF1 plus YF, right? So the equation 3, the third equation, there is no fourth equation, sorry. The third equation is just going to say this, that Z is equal to YF1 plus YF2. So can you just tell me what the first addend should be, maybe? Hello?
He's thinking.
Hello?
You have to repeat, Naveen. Your voice broke. I think his connection is...
Hello, can you hear me?
Yeah, now I can hear.
Okay, yeah, 1. The first one will be 1.
1, and then what will be the variable?
like uh, F1. Like,
YF1 you're saying?
oh wait. Uh,
Okay, just this will be. Yeah, so the first one, let's say,
no, it will be Z. Yeah,
okay,
Z.
sure.
Like,
Either way works, and then yeah, Z.
yeah.
Okay, so what is the second one?
Uh, yeah, -1 and YF1.
Right, correct. And then the third one will be -1 and YF2.
Yeah.
Okay, so now we have added all three equations to our solver. Now we need to add the ReLU constraint. So see, remember the ReLU constraint, in this case, just say what? They say that YF is equal to ReLU of YP, right? Now the way that you add ReLU constraint is by using this function, this add ReLU constraint. And in this function, you can pass the input query and you can pass the backward and forward variables, right? So if you come over here, you'll see that the ReLU constraint that they have is this. And here, 2 is the sort of the forward variable and 1 is the backward variable, right? And this guy takes back and then forward, okay? So the way you add, or the syntax is this basically. It's not solver, this will be inside Marabou code itself. And just checking the spelling is all right. Yeah. And then you can call this function with your solver. So you can do add ReLU constraint solver, and then you can put in the backward variable and then the forward variable, right? So you can
Diganta,
say, yeah,
and again, I'll have to take off.
yeah,
Okay?
sure.
So I'll let you continue. Don't end the thing, okay?
Yeah. I'll just
So
end
you
my
just,
recording.
yeah, correct. Yes.
Yeah.
Thank you. Goodbye.
Bye. Okay, so these are the two ReLU constraints that have been added. So is this all okay to you? So are we missing any constraints at this point? Do we have all the constraints? Let's set up a property that we want to specify. Let's say that x is going to be less than 5, and we want to show that z is also going to be less than equal to 5, right? Let's say that x is between 0 and 5, and we want to also show that z is between 0 and 5. So are there any constraints that we're missing right now? Nabin?
Like, what exactly do we want to show, like in this?
Right. The precondition is this. This is our precondition, and this is our post condition.
Okay.
So, okay, let me see. Have we added all the constraints that will encode the network itself? Is there any other constraint for the network that we need to add?
Like, I think we did not add the constraint for x, like smaller than equal to 5.
Yeah, we didn't add this constraint. We haven't added the preconditions constraint. That is correct. But we have added all the other constraints from the network itself, from any constraint that is from the actual network that we have already added, right?
Yeah.
As in things like, weights, biases, ReLUs, all of that is already added, right? So now all we need to do is add the precondition and the post condition, correct?
Yeah.
Yeah. So now notice that the precondition is a bound. The way you add bounds in ReLUplex is you'll have to just say, you'll have to set up some variable v, and you can only add upper bounds and lower bounds for variables. You cannot directly add something like ax plus b, y is less than equal to z. You can't add this, right? But you can directly add something like, let's say, x is less than equal to u and greater than equal to L, right? So this is allowed. This is not allowed directly. But you can always do something like this. You can always transform this by adding in another slack variable, let's say w, set up w to be equal to ax plus by minus z, and then say that w is less than equal to 0, right? So you can
Yeah.
add this as an equation constraint and then add this into Marabou, right? So in this way, you handle inequalities. Is this clear?
Yeah.
But notice that we are actually in a simpler situation where all the inequalities that we want to add, they're already directly on one of the variables that we have, right? We just have some bounds on x and some bounds on z, correct? So we can directly add the bounds on x. So let's see how we can do that. So the way you add bounds, again, if you go into this, you'll see that you can, so there is something called set lower bound and set upper bound. So inside this input query class, you will find this set, so let me see, it's probably down somewhere there. Yeah, see, there's this set lower bound function and the set upper bound function, right? The first argument it takes is the index of the variable you want to set the lower bound for. And then the second argument is going to be the actual floating point value, right? And similarly, there's the index of the variable, and then you have the actual floating point value, okay? So let's set up the lower and upper bounds for x. So there is the precondition. Let's say something like this. And let's say we want to set the lower bound for x and we want to set it to 0. And similarly, we want to set the upper bound. Okay, I think it's not bounds, but bound. There's no s at the end. And we want to set the upper bound for x to 5, right? So far, so good. Now, here is my question. How will you encode the post condition? Naveen? How do you encode this? Let's make it simpler, actually. Let's say that the post condition is z, just that z should be less than equal to 5. Okay. How would you encode this? Or I'll give you a hint.
I mean, can't we just use the set upper bound?
Sure. So what will you set z's upper bound to? You'll set z's upper bound to 5.
Yeah.
Is that what you're saying? Yeah. See, that will not work because if you pass it to Marabou, what will happen is Marabou will come up with an assignment for your variables x, yb's and yf's and z, such that all of your constraints are satisfied, right? So remember that Marabou is just the query that you're sending to Marabou is a SAT query, right? It is looking for assignment to all your variables so that all the constraints is satisfied, correct? So if you set z to less than 5, what it will do is it will just give you one value of x and corresponding values of yb1, yb2, yf1, yf2, and the corresponding output value z, such that z is less than 5, right? Does that really tell you anything about the property? No, right? Because what does it tell you? So in general, if I have something like if I want to say that, say I have got a function f that takes some x to z, right? And I want to say that, okay, if 0 is less than equal to x and x is less than equal to 5, I want to say that this implies f of x should also be less than equal to 5, right? Now, if I have some value of x, let's say some x equal to 2, for which we get z is also equal to 2, such that this thing holds, does that really tell us anything about this property?
Yeah.
What does it tell us? Does it tell us anything? No, actually it doesn't
Value
really
of
tell us.
x. That
Yeah. I'm
I
sorry if
mean,
I'm
like it
yeah.
just tells us that there is one assignment of
Yeah, it just tells
x
us that
that
there is one assignment of x for which this property holds. Whereas what we want to know is whether this is true for all assignments of x, right? So we are
yeah
interested in this, and if we pass this entire thing, to something like Marabou or Z3 for all that, what it will give us is it will give us one assignment of x, right? It will just give us one x for which this holds. But what we want
yeah
to say is that there is no x for which this does not hold, right?
yeah
So what we should do is we should instead pass it the negation of this property, negate this and then pass this. So we instead pass something like 0 is less than equal to x less than equal to 5, and that should imply that fx, or we say
greater
this,
than 5.
right, exactly. So negation of this would basically be this, and sort of implies, but it will be and fx will be greater
Yeah
than 5, right?
yeah
Now, if we pass this to z3 and z3 gives us some value of x, let's say that z3 gives us x equal to 2, for which z is equal to 6. What do we now know? We now know that this is a counterexample to this property, right?
yes
So we know that this property is false. On the other hand, if z3 gives us unsat, then we know that there is no value for which this property does not hold, right?
yeah
Yeah, so then we have proved this property. So the similar situation that we want to do over here. We want to set, if our post condition is actually z is less than 5, we want to set z is greater than 5 as the constraint over here. Is that clear?
yeah
Yeah. Okay. So let's do that. So let's post condition is z is less than 5, and then we want to negate constraint becomes z is greater than or equal to 5. So we want to set the lower bound. Correct? Okay. So now we have set up a solver. So now the final thing that we have to do is we have to actually call this solver, right? And the way that we do that
is
is,
there a way to set
yeah,
a strict upper bound or a strict lower?
right. So sadly, right now inside Marabou, there is no way of setting a strict upper or lower bound, but you can sort of simulate that by adding epsilon to your bounds, right? What you can do is, if you want to set a
Yeah
constraint like z is some constraint like, say, if you want to set if you want to set v is less than c, then you can convert this to v is less than or something like v plus epsilon is less than or equal to c, correct?
yeah
Yes, you can replace c with c minus epsilon, and then that will give you an over approximation, right? Because if this is sat, then this should also be sat, correct? But it is not
yeah
true the other way down. So you'll have to keep trying with smaller and smaller values of epsilon. So
Yeah.
this is the standard way of doing strict inequalities using weak inequalities. Yeah, and there is no like interface which Marabou gives us to do it more nicely. In fact, the Marabou algorithm, since it depends on simplex, and simplex again deals with weak bounds. It's not exactly direct to add strict bounds into Marabou very easily, right? So does that answer your question?
Yeah.
Yeah. So even simplex can't do strict bounds directly, right? Because in simplex, at any point, the assignment that you have, they actually satisfies the weak bounds, not the strict bounds, right? So in that sense, it's actually kind of hard, but you can do something like add an epsilon and then make your epsilon smaller and smaller.
Okay.
Okay. So we now have set the lower bound. So now what you need to do to actually solve this is you need to do this, you need to create these options, right? And what this options basically is there's this particular method called create options, and that is there inside, I think, Marabou utils, if I'm not wrong. No, it's inside Marabou itself. So yeah. So if you look at this create options, you can pass a number of different parameters, right? You can pass, the timeout, you can pass various different parameters with which you can tune the solver. So we're going to leave all of these to default in most of the situations. But the idea is that you can actually tune and fine tune the performance of the solver using all of these parameters. And that's why they let you, or rather ask you to create these options. So now when you have created the options, then you can just call solve, right? So solve, we create some options. Again, we'll have to import this thing from Marabou. Right? And then we have, let's say, assignment and status or result is equal to, and again, the solve function is also in Marabou core. And you have to pass it the solver or the input query that you had created and the options that you have. Correct? And then what we'll do is we'll print both of these things. Okay. So let's try this. So just a second. This seems to be some sort of an installation issue, but
Oh,
hmm, right. Uh, okay. So I don't know what the issue is right now. Let me actually just copy this thing to this particular flow. Hmm. Yes, so it seems that like there is some sort of issue with the installation that I currently have right now. I should have probably tested this, but I think that this was completely fine. But in any case, this is the code, right? And I'll post this to Moodle, and I suggest that like maybe run this on your machine and check that if it's producing the correct output. But what you're expected to get is basically something that looks like um, so if you look at this particular assignment, this assignment will basically have some sort of a dict with the or a list with the variable assignments for each variable if it was sat, otherwise it will be empty. So if this is empty, then it means that it's unset. If it's not empty, then it means that it's sat, and it like for each index in it, it will have the assignment for the variable with that particular index. So is it clear? I'm sorry that I wasn't able to demo this code, but is this okay so far? I think I somehow I
yeah.
messed up my installation while trying to run it in parallel on this other side, basically. So yeah, it's okay, right?
Yeah.
Yeah, okay. Definitely try to install this. They do have some examples over here. So once you've downloaded the Marabou folder, um, so if you go into right, so if you go into the Marabou folder, they will have some examples. And Okay, I'll send you a link to this particular example. So this Marabou code example.py, you will have it. It's there in the docs, and then you can try running this to test whether installation is running. Okay. Sure. Thanks. I'll end this
Yeah.
right now. Yeah. Do you have any questions?
Wait, like I have one question. Like I didn't understand like that. You added something create options. Like I didn't get what that was.
Right. So this. So you're talking about this particular line, right? So you did get everything, all the constraints and everything up until this point, right?
Yeah.
Yeah. Okay. Sure. I mean, of course, trusting me that this code actually works, but yes, this create options, what this does is that it will basically create some sort of a structure that carries a bunch of settings for the solver to like, or what settings the solver should use to solve it, right? So for example, you can set things like timeouts. I'll show you all the settings here. Just a second. Yeah, so if you go into the documentation, there is some settings over here that they say. So for example, you can set things like some initial timeout, right? And this is
Okay.
relevant to something called DNC mode, which we haven't gone into. Then, if you know that this Marabouoct or Reluplex, it does sort of splits, right? So you can set the initial number of splits. You can set the entire timeout in seconds for the entire operation, right? So if you set the timeout to something like 5, then after 5 seconds, no matter what, the Marabou will return and tell you that, okay, it couldn't find or whatever, right? So it won't keep like hogging your system. It will return after a while. Then there is all of these, splitting strategies that you can. So if you have multiple ReLUs that you can't fix, which ReLU do you split on, right? And then there are several heuristic driven strategies that you can choose. So all these sort of settings you can set up when you do a create options, right? So the idea is in this create options call, you can pass a bunch of settings over here. And then when you pass this options to the solve method, it will basically make sure that you use those options or that the solver uses these settings that you have set up in the create options, right?
Okay.
Is this okay?
Yeah.
Oh. Sure. So are there any other questions?
No.
Okay, sure. Okay,
Okay.
thanks.
Bye. Yeah.
Bye.